Okay, Module 18 is really going to be a hodgepodge. So far we have looked at reactions of alkenes that went through carbocation intermediates, and we looked at reactions of alkenes that went through halonium ion intermediates. Both of those were kind of generalized mechanisms that we could follow in a number of different examples. Um, in this module, we're going to look at other reactions, some of which you can follow the mechanism for, some of which I won't even show you a curved arrow mechanism for. But all of them are common reactions of alkenes that organic chemists would use to transform an alkene into different functional groups. And so with these, you're going to, while you should follow along with the mechanisms when they're shown, you really want to be able to understand the outcomes and predict the outcomes when you encounter them in new situations without necessarily having to go through an entire mechanism. Okay, so that's the overview for Module 18. We're going to start with a couple of reactions that look similar to one we've seen already. So earlier, we saw if we wanted to turn an alkene into an alcohol, we had a way to do that. Pause for a moment and think about what that is. Hopefully, you're able to remember that we could use water with an acid catalyst to carry out that transformation. If you need to for practice, go ahead and draw out the curved arrow mechanism and remind yourself what that looks like. What if we wanted to do these other possible transformations though? Suppose I wanted to make an alcohol, but instead of adding the OH to the tertiary carbon, I wanted to add the OH to a primary carbon. So far, you haven't learned a way to do that because this would be what we call an anti-Markovnikov addition, where we would put the more electronegative atom, the oxygen, on the less substituted carbon. You haven't learned any reactions that could carry that out yet. The second one, we also don't have a way to use because if we were to try using H2O and H+, remember we would go through a carbocation intermediate that would then undergo a carbocation rearrangement or an alkyl shift. And then that would give us a different product. So that would give us a product that looked like this, not the desired product in this case. So we don't have a way to carry that out either with no rearrangement. But organic chemists are clever. And when we have a reaction we'd like to carry out, we look for other ways to do it. Okay, so I'm going to show you two other ways to turn alkenes into alcohols. One will follow an anti-Markovnikov regiochemistry. The other one will still follow Markovnikov regiochemistry, but will avoid carbocation rearrangements. Okay. So the first one is the one that's going to avoid rearrangements. We call this oxymercuration reduction. It's a two-step reaction. So you first mix your alkene with one set of reagents, allow it to react completely. You get an intermediate product, and then you add a second reagent to finish that conversion. Okay, so this two-step process, oxymercuration, comes from the fact that we're adding oxygen and we're adding Hg or mercury in the first step, and then in the second step we're removing the mercury. So sometimes this is also called oxymercuration demercuration because the second step is removing mercury. So how does this work? This is not a mechanism I'd expect you to know. but it is worth showing so that you can see why it doesn't undergo carbocation rearrangement. So mercury is a metal, and metals, as far as we're concerned in organic chemistry, at least in an introductory course, metals are pretty much magic. You might see this on your periodic table for organic chemists that I wrote. In the middle there, metals are essentially magic for us. So mercury is going to play this magical role here where we're going to give it a lone pair, and we're going to allow it to undergo reactions similar to other ones we've seen, but it can have a lone pair or it cannot. It kind of gets to do its own thing. So we're using, in this case, mercury acetate. And just so you know, mercury acetate, that is an abbreviation for this. The OAC part is an abbreviation for what I've shown here. So in our first step, we're going to do something that's similar to forming a bromonium ion. And that is, we are going to have the carbon-carbon bond, double bond attack the mercury to oxygen bond, while at the same time, the lone pair on mercury is going to come back and form a three-membered ring. So what we get is an intermediate that looks a lot like a bromonium ion. This is just called a mercurinium ion. It behaves a lot like bromonium. It's a three-membered ring with a positive charge. We've seen a bunch of these before. When we have a three-membered ring with a positive charge, we're generally going to attack the more substituted carbon with whatever nucleophile is at hand. In this case, water is the nucleophile that's at hand. So I'm going to use water to attack the more substituted carbon and open up that three-membered ring. Okay, when I do that, it gives me this this organomercury intermediate. All right, that is essentially the mechanism for that first step. It doesn't undergo a carbocation rearrangement because there is no carbocation, right? This is more stable than a carbocation. So no rearrangement. So it's a way to do a similar reaction, but without going through that high energy intermediate. The second step here, where we add NABH4, that's going to follow a mechanism that is unlike any you're ever going to see, or at least in this class. So we will ignore the mechanism here as well. And just say that the NABH4 kind of acts magically to remove the mercury and replace it with a hydrogen. So notice the overall result. We do a Markovnikov addition of water to the alkene. All right, it's a Markovnikov addition of water to the alkene because to one carbon, we added OH. To the other carbon, in the second step, we add a new hydrogen, a third hydrogen. So we've added H and OH. We've added water to the alkene, and we did it in a Markovnikov manner where the oxygen went to the more substituted carbon. If I wanted to write this out, a lot of times you'll see this written over one arrow. So you'll have your alkene, in this case, this alkene. Over the arrow, we write step 1, mercury acetate and water. And in step 2, NaBH4. And as a product, we write the alcohol. So most often you'll see this sequence written over one arrow with step numbers. The step numbers are important because that tells the reader that we're adding these sequentially and not all together at once. One thing to notice about this that you'll see on this next slide is that this is very much analogous to the formation of what we would call a halohydrin or a bromo alcohol. We make a 3-membered ring in the first step. We attack it with water. We deprotonate, which I left out my deprotonation step here. So just for the sake of completeness, I'm going to go back and draw it in because that was silly of me. So to get to the organomercury intermediate, we do need to deprotonate this here. And that's what leads to that intermediate. Sorry about that. This is what happens when I get hasty. So this is very similar to a mechanism you've seen before. I don't want to dwell on the mechanism, though. I do want you to know this overall outcome of oxymercuration reduction. Markovnikov addition of water to the alkene, no rearrangement. All right, so that gives us one more option for turning an alkene into an alcohol with a little bit of a different outcome in some cases. Now, we've also seen that when we do reactions with water, a lot of times we can do an analogous reaction with alcohol, and that's also the case here. So just like we could react an alkene with an alcohol with an acid catalyst, we can do the same thing with oxymercuration reduction. In this case, we call it alkoxymercuration reduction, where instead of water, I'm now using an alcohol as my nucleophile. Okay. Essentially, the difference is instead of an OH group, now I get an OR group. So I'm making an ether. So in this case, I have an alkene. I'm reacting with an alcohol, and I'm making as a product an ether. Our standard oxymercuration reduction was an alkene reacting with water and producing an alcohol as the product. Okay, so perfectly analogous reactions here. Based on that, I think you should be able to predict the products of these 3 reactions. So I'd ask you to pause the video, come back after you've drawn your predicted products. One thing I'll point out, because you may or may not have seen this before, but this D down here at the bottom of the page, D is short for deuterium. It's just hydrogen with a neutron in it. It's a way that we can mark a specific hydrogen atom in a molecule. In terms of reactions, it will behave just like hydrogen. So you can just treat it like a hydrogen. I just included it there so that you would have to consider stereochemical considerations. I did mention, even though it's written on this slide, this reaction always results in a mixture of syn and anti addition. So you should consider that when you're predicting your products. So go ahead and pause the video and predict the products for each of these three reactions. Okay, so in this first case, I'm going to take my alkene. I am going to bond oxygen to the more substituted carbon of the two. Even though if I had a carbocation here, I would consider an alkyl shift to expand that ring. In this case, because I'm using oxymercuration reduction, I'm not going to do that. The oxygen that I add here is bonded to 1, 2, 3 more carbons. So I'm going to have those 1, 2, 3 more carbons hanging off here. I'm going to make an ether. This is an alkoxymercuration reduction. In terms of stereochemistry, if you want to consider it, I did create a new stereocenter. I'll make this a wedged bond, but I'll say, because I've made a new stereocenter, I'm going to get a racemic mixture of those products. All right, in this second case, now I'm using water, not an alcohol. So I expect my product to just be a Markovnikov addition and put an OH on the more substituted carbon. There are no stereocenters in the molecule to consider. And now this last one, I've got a ring here. So stereochemistry, I was told, would be a mixture of syn and anti. So I have some arbitrary choices to make. I know I'm going to add an OMe group to my more substituted carbon. So I'll add an OMe group here. That would still have a methyl group there. At this other side, I'll have my deuterium, and I'll add a hydrogen. Here I showed the OMe and the H adding syn, but this reaction will give a mixture of syn and anti. So I could also get the anti-addition product. And for each of these two, the syn product or the anti product, I would get it's an enantiomer. So this is going to be a mixture of 4 different stereoisomers. A lot of times if I were asking an assessment question about this, I would just say ignore stereochemistry because we're not going to get a specific stereochemical result. All right, so there's our overview of oxymercuration reduction. Okay, remember this was a way that we could carry out a Markovnikov addition to an alkene, but not have any rearrangements. What about this other outcome that we asked about before? Do I have a way to do an anti-Markovnikov addition where I add the OH to the less substituted carbon of an alkene? And the answer is yes, I do. This one's called hydroboration oxidation. It's another 2-step process, okay, where in the first step, we're adding one set of reagents, and then we add a second set of reagents in the second step. So this is your first example where you're seeing boron in a reaction. Boron gets used in specific ways because of its unique property. Take a look at your periodic table, and you'll see that boron has a very low electronegativity. So when I think about the structure of BH3, unlike most molecules, in most molecules, we would consider the hydrogen to be partially positive. Here, hydrogen is partially negative. And we're taking advantage of that fact. The boron is partially positive. Taking advantage of that fact in this case to add hydrogen with electrons rather than adding H+, which is what we normally do. So if we think about this reaction, I've got my alkene, and I'm going to do a Markovnikov addition in this first step. where I'm going to add, I'm going to have my alkene attack the boron, and the boron is going to bond to the less substituted carbon. That would leave a carbocation at the more substituted carbon, which is what we would want. It turns out a carbocation never actually forms in this case. So I have pi Cc donating to the empty non-bonding orbital on boron, but similar to some other reactions we've seen, at the same time, I'm going to have donation to pi star Cc. And this one might surprise you, but because of the low electronegativity of boron, it's the sigma BH bond that is a good enough donor to go ahead and attack pi star Cc at the same time. So in that step, we're making this intermediate where we're adding our new hydrogen and the BH2. In both cases, there was already one hydrogen there. So that still stays there. But we've added boron to one carbon and hydrogen to the other one. Okay. So boron gets added to the less substituted carbon atom because that leaves the partial positive on the more substituted carbon. This step follows Markovnikov's rule. The second step has a complicated mechanism. I will show that mechanism to you, but I'm not going to ask you to remember it or remember how it works. Again, all these reactions this week in this module, we're focused more on what is the outcome. So in the second step, we're adding hydrogen peroxide and a base. And effectively what it does is it replaces the boron with an oxygen. Okay. If you're interested in how that happens, here is the mechanism for that second step. You have your base deprotonating the hydrogen peroxide. When you deprotonate the hydrogen peroxide, now it's a good nucleophile. That's going to attack the empty p orbital on boron. And then you have this strange step that you would not have predicted. Oops. This strange step that you would not have predicted is that the boron, the carbon-boron bond actually slides over and becomes a carbon-oxygen bond. If you think about the donation, here we have sigma Cb donating to sigma star OO. And we're taking advantage of the fact that sigma star OO is a really good acceptor. And so then you can see the remaining steps here where the boron gets ejected. Not a mechanism I would expect you to predict, not a mechanism I would expect you to know. The thing I want you to take away is in this very first step, we're adding the boron and the hydrogen at the same time. So that is always going to be a syn addition. When you're adding two things at the same time, they're generally going to have to add to the same face of the alkene. So that'll generally be a syn addition. But the second step here is going to retain the same stereochemistry at this carbon. So if I consider the carbon here that I'm highlighting in purple, whatever stereochemistry it had with that carbon-boron bond, it's now going to have the same stereochemistry with the carbon-oxygen bond. So effectively, the overall result here is we're doing a syn addition of H and OH, and it's anti-Markovnikov. So generally, we would write this over one arrow where we could take our alkene. We would write step 1, BH3, step 2, H2O2 and OH minus. And the net result is we add an OH to the less substituted carbon and an H to the more substituted carbon, and we add them syn to each other. So in this case, if I had a methyl group there on that more substituted carbon, it will push the methyl group back. So again, it's another way to make an alkene into an alcohol, but now we get different regiochemical results. So we now have 3 different ways to turn an alkene into an alcohol, and they have subtle differences. We have acid catalyzed hydration, we have oxymercuration reduction, and we have hydroboration oxidation. Okay, so that's your first set of reactions to go with Module 18. Again, focus not on the mechanisms, but focus on what are the reactants, what are the reagents I'm adding, and what are the products that I get.